All right, so we're going to look at normal distribution. So that's the normal curve, and it describes many real-life data sets. So like SAT scores, heights of people, the number of miles before an automobile tire wears out, the size of a hamburger at a fast food restaurant. So normal curve properties are a bell-shaped curve, which we can kind of see there. It looks like a bell. It's symmetrical with respect to the mean, where the curve reaches its highest point. That's going to be our mean. And the mean, median, and mode of the distribution are all the same. The total area under the curve totals up to be a 1, and it follows the 68, 95, 99.7 rule. So inflection points are the point on the curve where the curve changes from being curved up to curved down. So, and vice versa. So here, what that means is this graph is curving up here, but at this inflection point, it starts to change its curve this way. In other classes, we call that concavity. So it's going this way, and then it changes and it starts to curve this way. So first it's kind of curving up, and then it starts to curve over. And when it starts to curve downward there, that's the inflection point. And it happens on both sides, because this is curving this way, and then it starts to curve out again. Now the 68, 95, 99.7 rule is 68% of your data will be within one standard deviation of the mean, so that's that area between those. 95% are going to be within 2 standard deviations, and then 99.7 will be within 3 standard deviations of the mean. We usually assume that we're dealing with an entire population rather than a sample when we're discussing normal distribution. So for example 1, the normal distribution and intelligence tests, suppose that the distribution of 1,000 students who take a standardized intelligence test is a normal distribution. If the distribution's mean is 450 and its standard deviation is 25, how many scores do we expect to fall between 425 and 475? All righty. So if we're looking at the information we've been given, for example 1, we are looking at the mean and the standard deviation. So we're going to take 450 and we're going to subtract the standard deviation, and we're going to take 450 and we're going to add the standard deviation. So what that does is it gets us the range. This is the range of data that is 1 standard deviation below and 1 standard deviation above our mean on our curve. So that tells us that it's a certain percentage. We're going to use that 68, 95, 99.7 rule. And what that means is 68% of our data is within 1 standard deviation. So we've got 0.68 because that is 68%, right? We have to change it to a decimal. And we're going to multiply that times the 1,000 scores that we have, and we have 680 scores that are between 425 and 475 using our 68, 95, 99.7 rule. So this was part A. Let's go look at part B. So part B asks, how many scores do we expect to fall above 500? Well, if we're thinking about what's going on here, we're looking at, it's got to be the part that's above 500. So let's see where 500 lands with our rule. If I take the range of data that we already had 1 standard deviation, and I do the same thing, so I have 425 minus another standard deviation is equal to 400, and then I have 475, and I do another standard deviation, I get 500. So we have a range of values here from 400 to 500 that are 2 standard deviations. So this is 1 standard deviation, this becomes the second standard deviation. So it's 2 standard deviations away from our mean, and we want to know how many fall above 500. Well, the 95% is our 2 standard deviations, but we want to go above. That's within. 95 will fall within the second. We need to know what's above it. So if we take 100% and we subtract out the 95%, that leaves us with 5% that are left. So again, this would be, let's go back to 1 standard deviation, 2 standard deviations. That's 95% of the rule. So that means there's a percent that's up here and down here. And understand that whenever we're talking, we're doing both the top and the bottom, above it and below it, and above it and below it, and we still have above and below. We only want the above. So with this, we're going to take our 5%, and again, 5% will be equal to 0.05 in a decimal, and we'll take that and divide it by 2 because we only want the part that's above it. We don't want the part that's below it. And when we do that, divide by 2, we will get 0.025, and this would be of the scores above 500. So now we'll take that 0.025 and we'll multiply it again times 1,000 and find that we have 25 scores above 500. So that's our answer for that. And understanding that these curves are kind of they're mirrors of each other a little bit in that respect, because they are the same on either side. All right, so now what we're going to do is discuss this a little bit. So in example 1, we estimated how many values within 1 standard deviation of the mean. And the z-scores are the area under the curve between the mean and a number. They represent the number of standard deviations the data value is from the mean. So in example 1, we found that for a normal distribution with a mean of 450 and a standard deviation of 25, the value of 500 was 2 standard deviations above the mean. Another way of saying this is that the value of 500 corresponds to a z-score of 2. So note that the table over here gives areas for only positive z-scores. That is, for the data that lie above the mean. We use the symmetry of a normal curve to find areas corresponding to the negative z-scores. So remember, it's symmetrical, so the positive and the negative, you're going to get the same z-score. The total area underneath a curve is equal to 1, so we can interpret the areas under the standard normal curve as percentages of the score values in the distribution. So here's our normal curve area right here. If this was like a 0 to a z, that's what we're talking about, is the area under the curve. On the chart, if it's z equals to 0.0 all the way down to 0.9, and then it goes from 1.0 to 1.9 and 2.0 to 3.0. When you have a third digit, that's where you find that the third digit is up here. So if you have like a 0.62, then you'll put those together. If you just have a 1.0, it goes with a 0.00 and it'll be right there. If you have like a 2.2 and a 0, it would go here. So you'll use the z-score table to figure out what you're looking for. So we're going to go on to example 2. So for example 2, we are given that z is equal to 0 and z is equal to 1.3. And it says to use the table to find the percent of the data, area under the curve, that lies in the following regions for standard normal distribution. Well, if z equals to 0, it's just going to be z equals 0. And down here we have 1.3. So 1.3 will get us a 0 there. So 0.4032 is what we're going to have. Because the other one is z equals 0, it starts there. So we're just doing this area here from the mean. So we've got, again, our answer was 0.4032. So this will be 0.4032. Changing that to a percent, we get 40.32%. So this is part A. For part B, we have Z is equal to 1.5 and Z is equal to 2.1. So this one was the area under the curve between the 0 and that. This one is not. It's between 1.5 and 2.1. So we'll find the area here, and we will subtract them. So the area for 1.5, so it's going to be 1.50. So it's 1.5 and 0 gets us 0.4332. So 0.4332. And for 2.1, we'll go down to our 2.1 with the 0 because we don't have a third digit or a second decimal digit. So we get 0.4821. 0.4821, and then we need to subtract them. So 0.4821 minus 0.4332 will get us 0.0489, which would be 4.89%. All right, let's look at part C. So for part C, we have Z is equal to 0 and Z is equal to 1.83, but it's negative. Now again, going from the 0, it's just right there, so we just have to find the other value. Now we don't have the negative, but remember the Z-score will be the same on one side as it is on the other, so we'll go find the positive value. So we have 1.8, and then because we have that second decimal of 3, we go to 0.03. So 0.03, come down. Well, let me, so you can see I'm coming from the 0.03, and I'm going to come down, and I'm going to meet the 1.8. And I get 0.4664 right there. So this will be 0.4664. Let me see if I can zoom in on this one. It's really hard because the numbers are so tiny. So 1.8 and 0.03. See that 0.4664? That's our answer right there. And because we're going from 0, we don't have to do the subtraction. We only had to do the subtraction on the previous one because we weren't going from 0. We were picking some kind of point in the middle over here. Alrighty, so with that, we again want to change it to a percentage. So we end up with 46.64%. Alrighty. So this kind of shows you what we were looking at. There's some pictures. So from 0 to 1.3, this was our area under the region, which was the answer we found. And then for the second one, this was the area for 1.5. This was up to 2.1. We wanted the area in between, and that's why we have to subtract out this area. And then for the last one, we were looking for this curve, but that's the same thing as this curve. They will be the exact same values. So we found the positive because it's the same as that one there. All right, the next thing that we want to do is we want to do some converting from raw scores. So if, to z-scores, if a distribution does not have a mean of 0 and a standard deviation of 1, we cannot use the table directly. However, if we first convert the non-standard values called raw scores to z-scores, we can use the table. So assume a normal distribution has a mean of mu. It's a special little u, but it's called mu, and a standard deviation of, that's omega. We use the equation z is equal to x minus mu divided by, actually I think that's sigma, so sorry. Doesn't matter. The little o with the little tail on it. To convert a value of x in the non-standard distribution to a z-score. So let's go do this one. And I think that is sigma. All right, it's a lowercase sigma, I think is what it is. Doesn't matter. So example 3, we're converting the raw scores to z-scores. In an effort to combat dog obesity, the Association for Pet Obesity Prevention has weighed a group of Basenjis, African barkless dogs, and found the distribution of their weights to be normally distributed with a mean of 20 pounds and a standard deviation of 3 pounds. We want to find the corresponding z-score for a dog in the group weighing 25 pounds and 16 pounds. So we're on to example 3, and we're looking at part A, 25 pounds. And we were given some information. So remember, we're having z is equal to x minus mu divided by sigma. So we need to know what our values are. First, we were told the mean. And the mean is our mu part. The mean that we were given was 20. And the standard deviation we were told is 3. So we're just going to plug in our values. So x is going to be the value we were given, which is 25, minus the mean over the standard deviation. So we'll end up with 5 over 3, which is 1.67. So all you got to do is find the parts, and remember this is our mu and this is our sigma. Alrighty, that's part A. Let's look at part B. So part B, we were asked to find it for 16 pounds. So that, and this is our x, just to make sure that we're following all the pieces. So z would be equal to, again, our x is 16 minus our mean of 20 divided by our standard deviation of 3, gets us negative 4 over 3. It gets us negative 1.33. All right, so example 4, interpreting the significance of an exam score. Suppose that to qualify for a management training program offered by your employer, you must score in the top 10% of those employees who take a standardized test. Assume that the distribution of the scores is normal and you receive a score of 72 on the test, which had a mean of 65 and a standard deviation of 4. What percent of those who took this test had a score below yours? Alrighty. So we're on to example 4. Let's figure out what we have. We have a score, which will be our x, which was 72. We were told that the mean, which again is our mu, is equal to 65. And the standard deviation, which is our sigma, is equal to 4. So our z-score would be our x minus our mu. So we've got our formula right here, minus our mu of 65 divided by 4. Well, 72 minus 65 would be 7. Divided by 4 gets us 1.75. Now we're going to use the table. So we'll go back to our table, and we're looking for 1.7 and then the 5 up there. So 1.7, let's zoom in just a little bit. We've got 1.7 and we're looking for the 5. So if we take the 5 on down, make sure we're in the right column, right here, and our 1.7. We end up with 0.4599 right there. So we have a 0.4599, which then translates to 45.99%. All right, now, we'll flip back to our problem. So what were we being asked again? Assume that the distribution of scores is normal. You receive this, which had a mean. What percent of those who took this test had a score below yours? Now remember that there's 50% of them that are below the mean, and then there's those that are above the mean. So yours is above the mean. Whoops, let me zoom it back out, so sorry. Because remember, it's on a curve. There's the above and below part. You were above the mean, and then you're in this percent up here. So you actually, because there's 50% of the scores were below it, you have to add 50% plus your 5.99% to get 95.99% that were below this score. Because on your z-score, you're finding the percent that's here. You have to add that whole percentage on that bottom half, and that's why we end up with that, adding the 50% that were below the mean. All right, so let's use z-scores to compare data. Consider the following information. Type Cobb hit this .420 in 1911. Ted Williams hit .406 in 1941. In the 1910s, the mean batting average was .266 and the standard deviation was this. In 1940s, they had a batting average, which is our mean, and the standard deviation was that. So if we assume that the batting averages were normally distributed in both of the decades, use the z-scores to determine which batter was ranked higher in relationship to his colleagues. So we're in example 5. First we're going to do 1910. Remember, our z is x minus mu divided by sigma. And we were told that our x for Ty Cobb was 0.420, and the mean was 0.266 divided by our standard deviation of 0.371. So this will get us 0.154 on the top divided by 0.371 gets us 4.15. So that's what Ty Cobb got. In 1940, we're looking at Ted Williams. And again, we're using the same formula. And his batting score was .406. And their mean was 0.267. Interesting that the means were similar. And the standard deviation was 0.326. A little bit difference in the standard deviation. So on the top, we're going to get 0.139 divided by 0. Oops, I'm missing a 0 here. Hang on. I left off a 0. So sorry. That makes a huge difference. If you're doing the math, you're like, that's not right. There should be a 0. Because I wrote the 0 in front, it threw me off. Sorry about that. So 0.0326 standard deviation. 30% standard deviation would be a lot. And then that would get us 4.26. So those are our two z-scores. So which one is better? Well, we can see that this one is going to be our better hitter. Watch your zeros. It's because I was putting the 0 there, but I didn't have it on my notes. So watch out for those zeros that should be in front of your values. It will totally change everything.